Okay, this is week 5. We're still in renewable energy, module 2, photovoltaic and solar thermal. Today we will talk about the photovoltaic performance and applications and try to complete the performance. We started with performance by discussing the IV characteristic at that time, the formula used for current and voltage, and then we moved into manufacture, biasing, and efficiency, cost. Now I will add one more point before I go for the application. So this week I will talk about application. Just to remind you, you remember we mentioned that we have silicon. Silicon is semiconductor. We have semiconductor, usually silicon or germanium. Okay, most of solar cell are either silicon or germanium, but mainly silicon. Okay, germanium almost very small fraction of the percentage. Okay, otherwise mainly silicon, and because it is available in our nature. And this silicon to be doped by impurities. Impurities could be donor type or acceptor type. Donor type, let me say, that metals or materials which have 5 electrons in the outer band. Example of this is phosphor or zinc as example. And acceptor, the material that accept to have electrons because it have only 3 electrons in the outer band, we call it acceptor. Example, boron and aluminium. And we put these impurities to come up with 2 type of layers. One of them P layer, as we said, and with the second positive layer, and the second one negative layer. Positive layer, which means it have holes, positive charge, and negative layer, which have electrons. And then when we put them together in this way as a sandwich, we come up with what we call it p-n junction. Most of our technology today is coming from p-n junction. Okay, we create the junction. Some of the electrons will cross. You know, the N layer contain electrons, is the major carriers. Okay, so some of the electrons will cross the junction to the P layer, and the same thing could happen from the P layer, which have positive charge as a major carrier. Some of the holes will cross in this way. Have a look. Let me just remind you. This has been discussed before, but just to remind you, this is the junction, this is the P, this is the N. Mainly here is the positive charge. Mainly here is the negative charge. Some of the negative charge will cross from P here. It creates, let me say, here potential, and the same thing for positive. Positive charge will cross the junction. This will not stay for a long period of time, just very small period of time. It's a dynamic, not a static, let me say, process. And it will continue until we reach equilibrium on the junction sides. And these electrons and holes drift, because you know, when we talk about free electron, we have, as I mentioned, in donor, we have 5 electrons in the outer band. One of them will be free, moving in the network in this way. So this electron is easily to be drifted by the other, let me say, p-type, P layer. And the same thing could be said for holes, which be drifted by. And there is also the diffusion of electrons from N side to the P side. These 4 currents, drift and diffuse, are represented by 4 formula, as you can see here, for diffuse of current of electrons from N to P, represented by this formula, and current drift from P to N by this. The same thing could be say for current holes and drift and diffuse from P to N and N to P. Now you may say, okay, what are these elements? These are currents. Okay, I understand these are currents. But what are these elements? These elements represent we are talking here, by the way, on the level of atom. Okay, we are talking about the level of atom, of the level of electrons. N and P, as you can see, represent the concentration of electrons, holes, respectively. Na is the concentration of the acceptor and donor, the impurities themselves. Ni is the intrinsic concentration. We're talking about the silicon itself, because intrinsic means the pure, the crystal. Dn and dp is the diffusion, okay, of electrons hole pair, and mu naught, mu p is the mobility of electrons and hole respectively. So it seems to be that we are talking about the concentration of electrons, holes, the intrinsic. We are talking about the mobility of these charge, negative or positive. Okay. For intrinsic, usually it's represented in terms of temperature, as you can see here. This formula, we use it usually to calculate the concentration of the intrinsic, okay, carriers. B is a constant related to effective masses, and T is the temperature, WG is energy gap, as you learned before, K Boltzmann constant, and T is the temperature. But as I mentioned, this drift and diffusion of currents from N to P, P to N, will continue. It's dynamic, as I mentioned, will continue until we reach equilibrium. It means the total electron or holes movement will be zero at the end. You see here, total current will be zero, okay, because there is no external potential difference apply across the cell itself. Now, if I substitute these currents from the previous slide, we have the formula, we substitute them, we are here. Now, this is E, represent potential difference between 2 points, which is represented from definition by minus dV over dx, rate of change of voltage with respect to the distance. So if I substitute, I simplify, I'm here, okay? Now I will take dP and P side here, make them subjective for the equation, and other elements to the right hand side. And let's define this part to be QKT. Then we have this formula. What this formula tell me? This formula tell me that ln P or positive or P negative will equal to voltage on P side, on N side, voltage on P side, the terminal. You know, this is the cell, okay? This is the cell. At the end, we have two terminal coming out from the current taken from these 2 points, positive and negative. So if I define this one to be contact potential VC, then we have formula for this voltage. Voltage of the cell equal constant, which is Boltzmann constant, T temperature, Q charge of electron, and then these concentration. We can represent them in this way also. It's equivalent. Let's take this and use it in the next example. The doping concentration of particular silicon junction is given Na, Nd. You see here, Na and Nd are given to you. The operating temperature 300, T temperature, as you can see here, 300. The intrinsic carrier concentration Ni is given also to you, okay? Others are constant, K and Q are constant. What is the contact potential Vc? I just need to substitute and I got 0.72. I would like to talk about this number. Have a look. Make it as a sense. The voltage across the terminal of a solar cell in the range of 0.7. If it is lower, 0.6, 0.5, this means that the quality of the cell you are using is not good enough, okay? Usually this is the standard, 0.7. You got it? And this is what available mainly in the market. Plus minus is okay, it's fine. Now, to model the solar cell, you know, physical systems or devices, we need to represent them mathematically. We model them, so we can't deal with them. So if I want to model the solar cell, I will say that the current produced by solar cell is number of charge of electron by number of electrons produced by the photons. And don't forget that we assume that photon coming, okay, if the photon HF energy is higher than the energy gap, it's to produce electron. Otherwise, it will not produce electron, useful electron going to the conduction band to be used in a current, electrical current. So here, number of electrons per unit area. If I represent it here, I will represent it current source, because we're talking about current, equal QA phi. Okay. Now, also, we mentioned that this is PN junction, so the diode, PN junction is diode. So we need to consider the diode effect here in the circuit. So I add diode here. Okay, current coming from here. Part of it is used in the diode effect, and part of it going to the load. Here I presented by resistance, could be anything, but load is like lamp, fan, whatever it is. Okay. Now I improve the current I will say that the current of the load here, okay, is the total current coming from the cell itself here, minus current going to the diode. This is Kirchhoff, from Kirchhoff voltage, current in equal current out. You study this in level 1. Okay. Now, for diode, we know the formula, which is called Shockley equation. It's well-known formula related to scientist. His name Shockley, and he won Nobel Prize in 1956, 58, maybe 58, yeah. And by the way, this equation is well-known and it's part of our modern lifestyle because it's part of our new technology. Okay, the focal point of time happened at that time when these people, Shockley and his group, they changed the world by inventing all, let me say, new technology. The world shifted from mechanical background into electrical and anything related to electrical, starting from communication, computer, blah 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 blah. So they changed the world. Lifestyle today now in our lifestyle today, technology is everywhere in our world. Technology mean electrical at the end. Okay, so this is the current. Okay, now this current represented this is the form of current. I can rewrite the current. This is current in terms of voltage. I can write it in this way: voltage in terms of current. Okay, just rearrange the equation. So we have equation for current representing the solar cell. One more issue need to be considered here. You remember when I talk about manufacturing the cell, what we mentioned? We mentioned we have fingers connected to the bars, bus bars. The bus bars taking the current to the contacts, two contacts at the end. It means the cell here, as you can see here, the cell at the end, we have P and N, two terminal, positive and negative. So this terminal is metal at the end. Inside fingers, bus bars are metals. So we have losses because they have resistance. You know, resistance is a property of any material. So we have resistances, so we have drop, voltage drop, we have losses. So if I consider this by subtracting minus drop in this resistance, I add resistances, I call it RS, series resistance. And then the equation in this way. By the way, also we mentioned to the open circuit and short circuit in previous sessions, okay, that when we have open circuit, no current flow. When we have short circuit, no voltage applied and no power at both. So no power production in both. Okay. Now, one more issue here is because of saturation current, because of the saturation current of the diode here, we have another losses, which is, we call it R shunt or parallel. It's large resistance. The current following here is very small, but it's also need to be considered. This is well-known model, which is called one diode model. Okay, the cell is represented by one diode model. There is another model which is two diode models, more advanced, but this is the one used today in many applications by many, let me say, softwares, organizations, designers, engineers. Now, this is the final form of the equation. As you can see, I talk also drop because of shunt, and both of them series also considered. So this is the final form of the equation. Now, also to remind you, you remember we mentioned to the IV characteristics, which look like this, okay? Now, frankly speaking, it's supposed to be rectangle in this way, but we lose this part because of the two resistances, okay? Here also we mentioned to the maximum power. You know, short circuit current, there is maximum current, which is less than short circuit. The same thing here. Short circuit voltage, there is maximum voltage. Now at maximum here, we have the maximum power. Okay. Now if I talk this in a very an index called fill factor, F, which tell me the quality of the cell itself. It's multiplication of I maximum, V maximum over I short circuit, V open circuit. Now, after we completed the performance, I would like to spend the remaining time in this session and next session just talking about the applications of photovoltaic. Mainly photovoltaic use in utility interactive systems, standalone system or tracker system. Utility interactive system is when we connect the system, PV system, to the grid. While standalone, we don't connect it to the grid, we connect it to specific load, isolated load, not connected to the grid. And tracking system, we follow the sun in this way. Now, people mainly use utility interactive systems. They connect the panels on their roof, okay, and they generate electricity and sell it to the electricity company. The same situation today in Oman. Now, the system is very simple system. We have PV models, put them together to make a panel array, and we have inverter. This is the grid. Sorry, this is the grid. It's supposed to be grid, not load. Okay. Load in case of standalone, but interactive system is supposed to be grid. Sometimes they put charger separate from inverter, or both of them in one, let me say, box. In isolated system, we may use battery. Okay. Now, many applications are there here. We are not talking. I will give examples from Oman. Okay, I will not go to Europe. Mainly in Oman here. Have a look here. This is the. If you go to Sohar City Center, you will find their parks. Okay, making shadow by using solar cell. This is a new technology by official, but at the end it's solar cell. They make a shadow for their parks, and at the same time they generate electricity and sell it. It's let me say, this practice used by many companies and factories everywhere in Oman, in the region. Example here, Sohar Aluminium, Valley, PDO, all of them. I mean, many companies are using PV panels in their parking locations to make shadow and at the same time to generate electricity. Also, if you remember Majan Electricity Company, they have this flower. I was the supervisor for this 50 kilowatt PV system, and now has been taken by Majis Electricity Company, and they install it there. Also, if you come to our lab here in Barka building, Sohar University, we have a grid connected system, we have a standalone system, tracking system. Okay, all these are available today in Oman. Okay, the system is very simple. We have PV and we have the inverter. That's all. PV and inverter. Everything else here, isolator, meters, these represent accessories. We just need PV and inverter wire, connect to the grid. Done. That's it. Very easy. You can read more about this in my book, my recent published book in 2019. I mentioned for it in this, in the references at the end of this session. Okay. Now, standalone system. The system now is connected to isolated load. Okay. This is the PV. Let me say this block represents the PV. Okay. Now, charger controller here to make sure that the voltage going to the load is smooth, because you know solar radiation is variable and the voltage produced is variable. We need to smooth it. Okay. Then we provide the energy required by my DC load. But if I have AC load, then I need to go for battery and then inverter to the AC load. This system is available in Sohar University on the roof of this building. These are other systems also available in Sohar University. Okay. Now, more applications. I will mention here for more application for using PV solar cell in standalone system to provide electricity for isolated places. Lighting is one of them. Many lighting applications. I will try to mention here to some of them as example. Lighting for billboard, highway form information signs, public use facilities, park lots, marines, homes, vacation cabin pair, and many other applications. Here, this is for lighting in Sohar University. This is for lighting in Masdar city in Abu Dhabi. Okay. Also here, this is in Istanbul, in Turkey. You can see here. Also here, this is lighting in Safa, in Abri and Safa, 1 million palm tree project. Okay, in the desert. This is a good application actually to use PV for. If you are in the desert and far away from the civilization, don't network there. What you do? Solar cell could be the best choice for you. Communication. Okay, for communicate. 1 second here. Just let me. Okay. For communication, if you go near the mountains here in Oman, you see some communication towers on the top of these mountains, and how do they provide electricity for their communication devices there. We cannot connect to the grid. It's really costly and difficult. And using DC generator, you need fuel. You have problem of fuel. Solar cell is the best option here. You can see here, this is in Haima. Has been taken in Haima, okay, for communication. There are many applications. They use it for communication application. Example, travelers, information transmitter, portable computer system, cellular phone, mobile radio system, and emergency call box. Also, remote site electrification. Some applications, okay, are available in remote sites, far from the cities, far from the civilization, from the grid. Solar cell could be the best choice as a source of energy. Example for these remote electrifications is houses in rural area or in villages, visitor center parks, park ranger site, vacation cabin, hunting lodge, remote farm workshop, village electrification, clinic and remote research facilities, highway research stops. I'm trying to read from the slide to show you this application. There are many public beach facilities, campground and military test area. By the way, why I would like to show or highlight some of the application, and there are many, because you need to know that solar cell is not only the cell we use it for our calculator. No, there are many applications for it. We just need to look to these applications and try to fit my system to this application. Remote monitoring system. Some systems are far from your location, okay? And there is monitoring system there. You need to you will put solar sensors. As example, you have weather station you need to monitor. You have some research equipment far away. You want to control them. How you provide electricity? You cannot put generator there. So the best option is photovoltaic. Example, meteorological information monitoring system, highway traffic conditions, structure conditions, seismic recording, irrigation control, scientific research, and some of them we already apply them by our students in many projects. This is example, okay, meteorological, let me say, weather station. And this is example in side from Kuala Lumpur. This is for park ranger. I took it there. Sign and signals, another also application. It's used in many navigational, background, audible warning signs such as sirens, highway warning signs, rail road signs. By the way, you can't read about them. It's used in many applications. If you see the some applications in the sea, in the ocean, how we provide electricity for them? If we want to make a lamp, small lamp flashing, cell, you put cell. This is the best option. You cannot put generator. You cannot put you cannot connect to the grid. It's in the sea, in the ocean. Also, let me say, airports far away from the city, okay? Photovoltaic could be the best choice for their electricity applications. Water pumping and control system. You know, we need water for irrigation. And if our, let me say, agriculture parts far away from the city, far away from the civilization, so how we can go to water from the well for irrigation? Because we use electrical pumps, electrical water pumps. We need energy here. Photovoltaic could be the best. It's used for a long time, talking about more than 50, 60 years back. Even in Oman, I know some people are using this in 80 decade. And some of them still until today, they use it in their parks, okay? One of our students in level 3, they got grants from Research Council of Oman at that time. I don't remember which year, maybe 14, yeah, 2014, okay? And they did a good work and they published some articles. I will try to drop on the Microsoft team some of these publications. This is one of their early published articles, Techno-Economical Assessment of Optimum Design for Photovoltaic Water Pumping System for rural area in Oman. They design, manufacture, and install, and test, and evaluate technically and economically water pumping system here in Suhar University. Okay, this is the PV, as you can see here. This is the PV, and this is the converter. The battery is connected here, and the energy sent to the load, which is here pump inside the well. This is the well, this is the water here. We take the water, either we store it in some store tanks, or directly it go to the irrigation here for the green area. And they evaluate for 1 year by calculation and by simulation and by taking experimental data record. Now I will try to show you the place they took at that time and how they change it. This is the place. You can see here. This is the place. This is the cover on the top of the well. Okay, it's, you see here rubbish and things, and this is the internal room. Okay, and they clean it with the help of some workers here. Okay, then they selected the panel that they design theoretically, and they use simulation software. These are the students work on the project, and they select the type of cell. And this is they make the frame in the workshop, so in the Faculty of Engineering workshop. Our colleagues, Mr. Rashid and Mr. Ibrahim Al-Ajmi, they left, and then they move the frame into the location. They make the concrete. Okay, they make the concrete here, as you can see, and they design, after they did their calculation, how many pipes we need. And they use here, if you can see, golden valve here. This is the electronic valves. It's open by automatically. Okay, and this is the panels. They put it on the frame. Okay, I cannot use my pen here. Okay, this is the panel. This is the pipes. This is the concrete. Okay, and here as you can see here, it's become with the concrete. These are the pipes. Okay, and it's connected to the monitoring system. This is the monitoring system. Okay, this is extra tank and charge pump to charge to save some water for irrigation if we want at night. And this is how it look like the area, and this is the final shape of the area. This is the panel, and the well is supposed to be somewhere here. Okay, they make a camera to monitor from distance on their mobile phone, so they can see what's going on, and they can control the signals here by sending some signals if they want to change the setting. Otherwise, the panel is smart. It know when to. By the way, it's follow the sun tracking and return back at the end of the day. It clean itself, auto cleaning, and capture the needed energy and generate the needed energy and send it to the pump and to these valves to work at specific time. They did all these calculations. Also, some of the applications are charging vehicles' batteries. Okay, this is, I took these photos in London. You can see here people there in the ships in the Tyne here. They put panels, and in their ships, their homes. They use the electricity produced by the panel. By the way, see the clouds, almost very small amount of solar radiation coming, but still it's enough. They use these two panels just to generate electricity needed for their application, charging mobile phone, watching TV, receiver, some small application, blender, and so other applications. It can be used for many applications related to charging vehicle, as example, firefighting and snow removal equipment, okay, agriculture machine and tractor and harvesters and so on. Disaster relief applications. Sometimes disasters occurred in some locations, as example, tsunami, earthquake, volcano, and so we need very fast to have a source of energy there. Because you know the infrastructure already destroyed. Let me say, get electricity shut down, everything distorted because of the disaster. Panel is easy, just put it, connect directly to the load. So it's a good option in this application. Cathode protection. Cathode protection what happened is, you know, when we use pipes under the ground, in the soil, or in under the ocean, and because of the soil and the ocean have a, let me say, salty salts, okay, salty water, soil. What happened is these metals get corrosion because of electrolytic action. Okay, it get corrosion, and we lose the pipes. So even in on oil pipes. So what we do, we need to avoid having electrolytic action. So we need small voltage, DC voltage, to avoid having this action and avoid having corrosion. So what we do, we use solar cell. It's very simple application. Just connect the cell through the day. We avoid having, as I mentioned, electrolytic action. Consumer products, many products we use them in our life can be used to supplied by solar cell. I mention always the calculator, small calculator, you use it in the school, and even today some of you are using. Also watch, lantern, calculator, radio, television, flashlight, outdoor light, security system, gate opener, gulf. Many applications are there. Okay, so I think the picture start to be increase because it's not anymore only the calculator. We have many applications. Okay, refrigeration. In some situation we need refrigerator, as example in a rural area or in the deserts. Okay, we have a small refrigerator. Okay, to save either food or medicine. And the people, they took it on the back of camels or donkeys or some other animals. So, but they need electricity. Battery is not enough. Battery will die in a short time. So cell, photovoltaic or solar cell is the best option. With my group, we designed a refrigerator in 2001, and this is just from one of our published article. As you can see, this is refrigeration. All these are accessories of the system. And this here you can see a small refrigerator designed by our students in Sahara University. This is another cooling system, and this is air conditioning. Okay, I will talk about them later on, inshallah, when we reach the solar thermal part. This is air conditioning using solar photovoltaic. This is cooler. Our students participated in Sultan Qaboos University gathering there. Now I will complete this example and stop here, then to continue in the next session. If we till now we talk about solar cell, okay, and we put it together, these cells, as you can see here, to make a module. Put them here in series and parallel to increase the energy and voltage current. And panels, we put them together, these modules to have panel. We put panels together to have array or power plant. We understand also series and parallel. When we connect series, we increase the voltage. Similar to the batteries, we connect batteries together to increase the voltage. Or we connect them parallel to increase the current. The voltage will be the same. You understand this from secondary school and even from level 1. Now, also you remember we mentioned that the voltage of the cell, it could be 0.7 in this range, 0.7, 0.6, 0.5 in this range. Okay. But our PV panel usually 12 volt or 18 volt. How we increase the voltage? Our panel have high power, high current. How we can do this? Have a look at this example. Photovoltaic cell are to be arranged to provide an output 12 volts. I need 12 volts. Okay. And the power 120. If the voltage and current at maximum power is 0.49 volts and 5.1 ampere. If I multiply them, by the way, I got the maximum power. This is voltage, this is current, and this is power. For one cell, recommend an arrangement that meets the specification. Okay, how can I connect these cells to come up with 12 volt, 120 watt PV panel or module, module. Now I will say, okay, I want 120 watt. One cell, give me how much watts? It gives me 2.53. So let me divide 120 divided by 2.53. It tells me that I need around 47.2 cells. We need to approximate it, make it as example 50 cells. Okay, so I can get the 120 watt. What about voltage? We need 12 volt, okay? And the cell voltage is around 0.49, around 0.5. So I divide 12 volts over 0.5. It tells me that I need to put 24 something cells in series to get the 12 volts. I will approximate it to 50. Let's approximate this into 25, sorry, 25. So this means I need to put cells in this way, okay, connect in series. Let me make it as a circle rather than square. In series into 25 cells, okay? It will give me from this point to this point 12 volts. You got it? Okay, but just a minute, I need 50. We say 50 cells. This is 47. So this means that I need to put here another, let me say, bench, okay, together in parallel. The voltage is still 12 volt. This is 0 to 12, but the power current here increase here and here. It will give the 120 watt. If I do the right calculation, 25 in series and 2 branch in parallel, then I got 50 cells, then I got 126.5 watt. I will stop here. I will stop here. Do you have any question